Hi everybody. In this video I want to first explain what a derivative is. I'll then present a few useful results. After that I'll do a few examples, and then finally at the end I'll use one of those examples to do a spot check of two of these useful results. Alright, so here we go. Imagine that y is some function of x, and that a plot of y of x versus x looks like this blue curve. Great. The derivative of y with respect to x, which I can write as dy over dx, and which I pronounce dy dx, the derivative of y with respect to x is represented precisely, graphically and geometrically, by the tangent line to this curve at the point corresponding to x. So let me explain what a tangent line is. A tangent line I can take by just taking a straight edge, having that straight edge graze the curve at the point of interest and only at the point of interest, and then drawing a line along the straight edge. So the slope of this tangent line turns out to be exactly equal to the derivative of y with respect to x at the location x. Again, this is a precise geometrical representation of what a derivative is. However, without a little bit more mathematical technology, we can't really use it to effectively calculate derivatives, because what we would have to do is plot y versus x for whatever function we're interested in, and then at the value of x where we want to know the derivative, draw a tangent line and then calculate the slope of that. And if we wanted that information as a function of x, I'd have to do that for a bunch of different x's, and then somehow stitch all that information together and then try to write a function that matched it. All right? Not very practical. What we need is an analytical formula that'll help us calculate what the derivative with respect to x is of the function y from the form of the function itself. All right, and that formula is right here. Here's what it says. The derivative of y with respect to x is defined as, and that's what the triple equal sign means. It means is defined as the limit as delta x approaches 0, I'll discuss that later, of y of x plus delta x minus y of x over delta x. All right, so there's got to be a picture that goes with that, and I'll get to that in a moment. But first, I've got y of x plus delta x minus y of x. We can shorthand consider that as a delta y. All right, so we've got a delta y over a delta x. That looks like we're trying to calculate the slope of something. All right, let's see what that represents. All right, so let's take this and look at a picture over here. And I need to update this picture, which I'll do momentarily. All right, so here's x, the location, the value of x for which we want to find the derivative of y with respect to x. We go up to here on the curve. So this is y of x. I can go over delta x sub a to this location here, x plus delta x sub a. That's the x value corresponding to the point a that I've added to this plot. All right, that value on the y versus x curve corresponding to this value of x would be y of x plus delta x sub a. All right, so the difference between this y value and this y value, y of x plus delta a minus y of x, that goes in right here, all right, where I'm using delta x sub a instead of just delta x. All right, so that's my delta y sub a. That's my rise between these 2 points. Now, going from here to here, that's my delta x sub a. That's how far this location of x is from this one. All right, so that's my run. So taking my rise over my run, I can calculate the slope of the secant line. And the slope of that secant line is given by this with delta x being replaced by delta x sub a here and here. Great. Now you might say, wait a minute. I thought we were supposed to be calculating the slope of this curve at this point here. This secant line that I've just calculated the slope of and represented right here doesn't look like it has anything to do with the slope of this line. All right, well wait, we haven't yet taken account of the limit as delta x approaches 0. So we're going to now start to do that. Imagine instead of this point A, I picked another point right here. So instead of having a delta x sub a, I have a smaller delta x. All right, so I'm going to update my plot to show that. So here's my point B. That's located on the plot at the value of x plus delta x sub b. All right, so this distance here is delta x sub b. That's the run between the original point on the curve and this point B. The rise is given by the difference between y of x, which is still here, and then the y value corresponding to this. So if I go up here and go over there, that's y of delta of x plus delta x sub b. All right, I can call that shorthand delta y sub b. All right, this minus this is this. That's in the numerator here, where instead of delta x, I've got delta x sub b, or all of this I could call delta y sub b. And then the run is delta x sub b here. So from going from here to here, delta y sub b is the rise, delta x sub b is the run. The rise over the run will give me the slope of this new secant line. And we can see this new secant line is a much better approximation to the tangent line than the original secant line was. All right, so it's still an approximation. But we're not done. We can imagine repeating this process over and over. So I could take a smaller delta x, and a smaller delta x, and a smaller delta x. And I have another point on the curve that's ever closer to this one. And the slope of the corresponding secant line is going to get ever closer to the slope of the tangent line. All right, so it might seem that really this, what I've just generated here, is just a good enough approximation method. If I want a better value for the derivative, a better approximation, just take a smaller delta x. And that's true. You could apply this numerically and do this for a good enough numerical approximation. But it turns out with a precise understanding of what a limit is, and that comes from Calculus 1, and so I'm not going to do it here because I can't really do justice to it in this short presentation. With a precise definition and justification and understanding of what a limit is, this turns out to be an exact expression. In the limit, as delta x squeezes down to 0, this, which gives you the slope of the secant line, approaches and then becomes exactly the slope of the tangent line. So it turns out that if we sharpen up our understanding of what a limit is, again, I refer you to your past, present, or future Calculus 1 course, that this becomes an exact analytical expression that can be used in principle to calculate the derivative of any well-behaved function. Okay, having described or attempted to describe what a derivative is, I now want to go into some useful results. The first useful result is that the derivative of any constant is equal to 0. And we can get that by looking at another plot. So all the way up here, I've plotted a line y equals a, where a is some constant. All right, that slope of this line is going to be equal to 0. And since derivatives can also still be thought of as slopes, we get the result that the derivative of any constant is equal to 0. Great. Rule number 2, I'm going to state without proof. Rule number 2 also relates to constants. So here again, a is again going to represent a constant. This time I have my constant a multiplying some function of x. If I take that product and then take the derivative with respect to x of that product, the result will be a, the constant out front, times the derivative with respect to x of f of x, my function of x. All right, so in effect, what happens is a multiplicative constant slides through the derivative operator, and then the derivative operator just operates on the function of x. The third rule I'm also going to state without proof. This third rule is a shortcut rule for calculating the derivative of a specific type of function. All right, so the specific type of function is x to some power of n, where n is a real number not equal to 0. The derivative of x to the power of n with respect to x turns out to be n times x to the n minus 1 power. So basically, the n comes down and gets decremented by 1. All right, this is a shortcut rule. So if you have a function of this form, you don't need to go all the way back to the definition of the derivative to try and calculate it, which I haven't even really shown you how to do. You can just plug it into this formula and use it. And this is a specific example of something that happens over and over in calculus. We use the definition of the derivative not usually for calculating derivatives of functions, but instead we use the definition of the derivative to derive shortcut formulas for calculating derivatives for different kinds of functions. All right, so in Calculus 1 and Calculus 2, a lot of time is spent using the definition of the derivative to derive shortcut formulas for calculating derivatives of various kinds of functions. This is just one of many examples. It happens to be really, really useful at the beginning of introductory physics, and so I wanted to show that right now. All right, before moving on to some examples, I want to make one more point. I've talked about y as a function of x, but really we should be thinking more generally about dependent variable and independent variable. I might have functions of an independent variable that I don't want to label x. Maybe I want to call it z. Maybe I want to call it t. Maybe I want to call it w. All right, we don't always have to use x. And so these formulas can always be rewritten or recast in terms of a different independent variable. So just to give you an example, imagine I have some function t to the power of n. The derivative of t to the power of n with respect to t is equal to n times t to the n minus 1 power. All right, this formula is exactly the same as this formula. Really what this formula says, either one of them says, if I have some independent variable to some power, if I take the derivative of that function with respect to that same independent variable, I'll get n times the power n times that independent variable to the power n minus 1. All right, that's what it says in more generic terms. So really, this isn't a new formula. These are the same formula. All right, let's do some examples. All right, consider the function y equals 2 times x to the 5th power. Let's take the derivative of y with respect to x. All right, so the derivative of y with respect to x, I take the derivative with respect to x of now my specific function of x, which I plug in. All right, now using rule number 2, or useful result number 2, this leading constant slides through. And now I can use rule number 3 right here. The derivative with respect to x of x to the 5th is 5 times x to the 4th. And my result is equal to 10 times x to the 4th power. Great. All right. So given a function y equals 2 times x to the 5th power, the derivative of y with respect to x is 10 times x to the 4th power. Note that the derivative itself is a function. All right, here's another example. Z equals 3 times t to the 4th power. So now my dependent variable z, my independent variable is t. All right, let's calculate the derivative of z with respect to t. Derivative of z with respect to t, I start by plugging in my function 3t4 to the 4th power for z. I've done that right here. I can then use useful result number 2 to pull the 3 through the derivative. I can then use useful result number 3 to take the derivative with respect to t of t to the 4th power. I'll do that right here. And finally, I get that the result is 12t cubed. So for z equals 3 times t to the 4th power, the derivative of z with respect to t is 12t cubed. All right, let's do one more. Given a function y equals 1/4 x squared, let's calculate dy dx, that is the derivative of y with respect to x. First, we plug in 1/4 x squared for y. Next, we use useful result number 2, and the 1/4 factor flies through the derivative operator. All right, and finally, using useful result number 3, we can take the derivative with respect to x of the function x squared, which will give us 2x. So I'll have 1/4 from this and a 2x from this. And finally, we get that the derivative of y with respect to x is equal to 1/2 x. All right, just to summarize, given the function y equals 1/4 x squared, the derivative of y with respect to x is a new function, 1/2 x. So the function 1/2 x should give the slope of the original function 1/4 x squared on a y versus x plot for every value of x. All right, so I want to use this example to check out rules 2 and 3. All right, so rule number 2, I've got a leading factor in my function, so I've got a function of this form. And rule number 3 relates how to take the derivative with respect to x of that function that I've got in here, all right, for the particular value n equals 2. So what I'm going to do is this. I want to show for a few specific values of x that if I plot this function, that then this formula does indeed give me the slope of this function at selected points. All right, so I'm going to do that right now. Here's our original function, y equals 1/4 x squared. If I take the derivative of that with respect to x, I get 1/2 x. So 1/2 x is a function that gives the slope of our original function for every single x. Now that's pretty amazing. I can't actually prove that, but what I can do is do a reality check of this claim for a few values of x. So let's check it for x equals 1, x equals 2, and x equals 3. All right, so here we go. When x is equal to 1, I can plug that in for x in our original function, and I'll get y equals 1/4. I can also plug in x equals 1 into our derivative expression. I'll get dy dx is equal to 1/2 when x is equal to 1. So what this says is that on our original curve at the location x equals 1 and y equals 1/4, that's at this black dot right here, that the slope should be 1/2. All right, so to check that, I've plotted this red line, which has a slope of 1/2. And how do I know the slope is 1/2? I'm using the y equals mx plus b slope-intercept formula. This line has a slope of 1/2. It looks like this red line really does, in fact, have the same slope as this blue curve right at this location, x equals 1, y equals 1/4. Now, if we want, we can check the slope of this red line by hand if you don't trust the plotting program that I use to produce this. So we can get the slope from any 2 points on the red line. Let's pick this point and this point. Going from here to here, the run is 1 and the rise is 0.5. So 0.5 divided by 1 gives me 0.5, which is equal to 1/2. So that's consistent with the claimed slope for this line, which seems to match the slope of our original blue function at this location. All right, so it seems to check out for x equals 1. Let's check for x equals 2. When x is equal to 2, I plug that in here. 2 squared is 4. 4 divided by 4 gives me 1. So when x is equal to 2, y is equal to 1. If I plug in x equals 2 here, 2 divided by 2 gives me 1. So dy dx also has a value of 1. So what this means, what this claim is for this line of the table, is that at x equals 2 and y equals 1, which is at this black point, that the slope of the original blue curve, y equals 1/4 x squared, at this point should be 1. So to check that, I plotted a line, this green line, with a slope of 1 and a y-intercept of -1, which you can see is way down here. And that line, the y-intercept was chosen, so this line of slope 1 would go through this point, so we can see whether the slope matches that of the blue curve. It does indeed seem to match. So this green line of slope 1 seems to nicely match the slope of this blue curve at this point, which is the claim. Now, if you don't trust the plotting program, we can check the slope of this green line by hand but with any 2 points. Let's use this point and this point. So there's a run of 1, a rise of 1. 1 over 1 gives me 1. It all seems to check out. All right, let's check finally for x equals 3. When x is equal to 3, I'll have 3 squared, which gives me 9 divided by 4. So y will be 9/4 when x is equal to 3. Plugging in x equals 3 in our derivative expression, we get that dy dx for x equals 3 is 3/2. So what this line says is that at x equals 3 and at y equals 9/4, and 2.25 is just the decimal expression for 9/4, that the slope of our original blue function, y equals 1/4 x squared, that the slope here should be 3/2. To check that, I plotted the black line. This black line has a slope of 3/2 and a y-intercept chosen so that a line with slope 3/2 will go exactly through this point. And we can see that at this point, the slope of the black line nicely matches that of the original blue function. And again, we can also check the slope of this black line by picking a couple of points on the black line. Let's pick this point and this point. Going from this point to this point, the rise is 1.5. The run is 1. Rise over run would be 1.5 over 1, which is 1.5, which is 3/2. And so it checks out. All right, so hopefully this helps give you some confidence that if you take the derivative of a function, you get another function that gives you the slope of the original function at every single point. Very cool. All right, that's all for now. I hope this review, or preview, whatever the case may be, will be useful to you in your study of introductory physics. See you next time, and thanks for watching.